Hello and welcome to lesson number 25, Mathematical Induction. If you're wondering why I'm wearing glasses, it's because recently I had a corneal cross-linking surgery done on my right eye and I've been recovering for the past week or so, and now I'm better now. If you're interested in what corneal cross-linking is, check the links in the description down below. And anyway, I'm back and we can restart going on with mathematical lessons. Lesson number 25, Mathematical Induction, is going to be shorter than most of the recent videos that I've been posting because its concepts are quite simple compared to the rest of the videos. Mathematical induction has to do with statements. Consider a statement S evaluated at a certain value x. What I mean by this is that x is an input into a statement S which could make statement S either true or false. Statement S could be something like x greater than 0, in which case x equals 1 will give a true statement. X equals negative 1 will give a false statement. X equals 0 will also give a false statement since 0 is not greater than 0. Now then, given such a statement structure, mathematical induction relies on two basic principles. The first principle is the principle of a base case. For some statement S, if we know that for some value x0, statement S is true, we can move on to the second principle and use it to establish mathematical induction. So first off, for principle number 1, we need a base case, as in we need some basic value of x0 for which the statement S is known to be true. Now given this, the second principle is what I like to call the mathematical induction step or induction method. In this, what we need is basically a rule that says, given some x, let's say xn, if we know that, as in if S of xn is true, we can somehow mathematically prove that S of x sub, let's say n plus 1, is also true. Mathematically, we have some logical system that we can use in order to show that given a certain x, which I'm going to call x sub n, is true, we can then show that for the next value of x in that set of x's, which is represented here by x sub n plus 1, S of x sub n plus 1 is also true. So it should be noted that the mathematical rule that defines x sub n plus 1 relative to x sub n can be anything. Any valid mathematically definable relationship between x sub n plus 1 and x sub n could be established in mathematical induction. However, in our A level, the most likely relationship that you will see is that x sub n plus 1 is x sub n plus 1, as in the next integer. However, it should be noted that you can do this for any value you want. It does not have to be the next integer, as in x sub n plus 1 does not have to be x sub n plus 1. It could be x sub n times 2 or n times x sub n or anything like that. Any kind of relationship like that could be used in mathematical induction. The basic principle we need to have is that we have some base case for which a statement S is going to be true, and then given this, we also need to have some kind of mathematical rule that we can prove where, given some certain x in a set of x's, if we know that that S of that particular x, which is x sub n in this case, is true, then we can say by some method provably that S of x sub n plus 1 is also true. Using these two principles, what we can see is that if S of x0 is true, it implies that the next value of x, as in S of x1, is also true. And then if S of x1 is true, it implies that the next x, which is S of x2, is also true, which then implies that S of x3 is true, which implies that S of x4 is true, and so on. So basically, this kind of acts as a domino system. We have a first domino, which is our base case. Kicking this domino, given that we know that hitting one domino will hit the next domino, as in hitting S of x sub n will hit S of x sub n plus 1, we can say hitting the first domino hits the second domino, which will then hit the third domino, which will then hit the fourth domino, which will end up hitting every single domino. So basically, S of x0 is true, which implies S of x1 is true, which implies S of x2 is true, and so on up to infinity for all values of x for the given rule between x sub n and x sub n plus 1 and the given base case x sub 0. This is all the theory that we need to discuss in mathematical induction. It's really that simple. However, since the rules that we can use for mathematical induction and different ways that we can prove statements in mathematical induction are varied, this video is actually going to contain mostly different example questions where we use mathematical induction to prove certain statements true for certain values of, let's say, x or n. So then, let's go and take a look at some of those examples and see how we can use mathematical induction to prove them. For our first example problem, let's prove that n factorial is greater than 2 to the power of n for n element of the integers and n greater than 3. In order to solve this kind of problem, the first thing we're going to do is establish the set of values for which we need to solve it for. In this case, we have n being element of the integers, so it's like 1, 2, 3 and so on, but n is greater than 3. This limits n to the set of 4, 5, 6, 7, 8 and so on. Since n has to be an integer, but n is also bigger than 3, so n is not equal to 3. The next integer after 3 is 4, so n could be equal to 4 and 5 and 6 and so on. Using this set, we can now establish the base case that we want to prove for and also the rule that connects the term and the next term after that. Here we can see the first number, the lowest number is n equals 4. Generally, the lowest number will be the number that you want to pick for your base case. Sometimes it will be the highest number in an infinite set. If it's a finite set, then you can probably pick somewhere in the middle. But for our purposes, we're going to be picking n equals 4 as our base case. As for the rule, we can see that every next number is 1 plus the previous number. Therefore, using the rule 1 plus the previous number would be a good rule for us to establish our inductive step. So to start off with the base case, what we're going to do is consider the base case value of n equals 4. So we're going to write consider n equals 4. For n equals 4, we're going to try to prove whether this statement is true or false. To do that, we're going to consider the left hand side and right hand side separately. The left hand side of the inequality is n factorial, which in this case is going to be 4 factorial. 4 factorial is going to be 4 times 3 times 2 times 1, which is going to be 12 times 2, which is going to be 24 times 1, so 24. So 4 factorial, or the left hand side, is 24. As for the right hand side, RHS is going to be 2 to the power of n, which is going to be 2 to the power of 4. 2 to the power of 4 is 2 times 2 times 2 times 2, which is going to be 16. So the right hand side is going to be 16. Here we can clearly see that the left hand side 24 is greater than 16. So we can say, since the left hand side is greater than the right hand side, the statement is true for n equals 4, as in our base case. So we can say true for n equals 4. This is going to be our base case. Now that we've established a base case, let's try to establish the inductive step and use that together with the base case in order to prove this inequality here true for all of these n's that we want to show for. So what we're going to do in order to establish our inductive step is to assume that for any element of this set, the statement is in fact true. So we're going to assume for some element of this set, the statement n factorial greater than 2 to the power of n is true. Given that assumption, we're going to then show that it is going to be true for the next number n equals that previous number plus 1. So to do this, let's say let n equal to p, where p is an element of the set that we want to prove for. So we're assuming that for this set, this result here, n factorial greater than 2 to the power of n, is true. So p needs to be an element of the set Z, and p also needs to be greater than 3. So p is an element of the integers and p greater than 3. For this, we're going to assume that when you substitute n for p, so instead of n factorial, we substitute p factorial. Instead of 2 to the n, we substitute 2 to the p. When we do that, we're going to assume that p factorial is in fact greater than 2 to the p. So this is our assumption. We know it's true for at least one of the values. It's true for n equals 4. We don't know yet that it's true for all of the values, but we're going to assume that it is such. So for some n element of the integers and greater than 3, we're assuming that p factorial is greater than 2 to the power of p. This is going to be our assumption for our certain value of p, a certain value of n. Given this, we're going to see if it's going to be true for the next value, which is going to be n equals p plus 1. So what we're going to do is consider n equals p plus 1 and see if, given that it's true for n equals p, it's also going to be true for n equals p plus 1. So for n equals p plus 1, the left hand side that we need to figure out is going to be n factorial, which is going to be p plus 1 factorial. So this is going to be equal to p plus 1 factorial. As for the right hand side that we need to figure out, the right hand side is going to be 2 to the power of p plus 1. Now generally in inductive processes like this, we're going to be using the previous step's result in order to prove the next step to be true. In this case, we need to somehow use the fact that p factorial is greater than 2 to the power of p. I'm going to be doing that by breaking the p plus 1 factorial into p plus 1 times p factorial. This is of course true since p plus 1 factorial is equal to p plus 1 times the number below it, which is equal to p, times the number below it, which is p minus 1, times the number below it, p minus 2, all the way down to 2 times 1, and all of this stuff here is just p factorial. So therefore, p plus 1 factorial is in fact equal to p plus 1 times p factorial. Then I'm also going to look at this thing and break this again using index rules, using this p plus 1 as 2 times 2 to the power of p. We can see that that's true since p plus 1 power just means multiplying 2 by itself p plus 1 times, which means we need to multiply 2 by itself p times and then multiply by another 2. So now we have that the left hand side is p plus 1 times p factorial and the right hand side is 2 times 2 to the power of p. What we know from our previous step is that this value here is bigger than this value. What we're going to do now is to show that this value p plus 1 is greater than 2, and then we have a bigger number here, as in this number p plus 1 is bigger than 2, and then multiply that by another bigger number p factorial which is greater than 2 to the power of p. So then what we're going to do is use the logic that here we have two bigger numbers being multiplied by themselves, which is definitely going to be bigger than two smaller numbers multiplying them by themselves. Something like 8 times 5 is definitely going to be bigger than 2 times 3, since 8 is bigger than 2 and 5 is bigger than 3. So to do that, we're going to consider p plus 1 and 2, since we already know that p factorial is bigger than 2 to the power of p. So here, we know that p plus 1 is bigger than 4, since p is bigger than 3, which is one of the conditions that we established. We established that p has to be greater than 3. So for p greater than 3, p plus 1 is bigger than 4, which itself is bigger than 2. So we can say, therefore, p plus 1 is definitely bigger than 2. So here we've established that p plus 1 is a bigger number than 2. From the previous result, we already know that p factorial is bigger than 2 to the power of p. We need to also establish that these are all positive numbers. We're going to say greater than 0 here. We're also going to say that p factorial is greater than 2 to the power of p, which is also greater than 0. The reason we need to do this is because if p factorial was a negative number and p plus 1 was a negative number, and 2 to the power of p was a negative number and 2 was a negative number, it's not true, but we'll just assume that's the case. If that was the case, it would be possible to have something like negative 1 times negative 3, let's say, and negative 5 times negative 8. Here, negative 1 is definitely bigger than negative 5, and negative 3 is definitely greater than negative 8. But if we consider the products, negative 1 times negative 3 is 3, and negative 5 times negative 8 is going to be 40. So therefore, it is actually the other way. In order to avoid this, we need to make sure that everything is positive. And in our case, everything is positive, so there's nothing to worry about. But we still need to state it, otherwise we would kind of be wrong. So now that we've stated this, since we know that p plus 1 is bigger than 2, as in this term is bigger than this term, and we also know that p factorial is bigger than 2 to the power of p, the product of the two bigger numbers is going to be bigger than the product of the two smaller numbers. We can therefore say that p plus 1 multiplied by p factorial is going to be bigger than 2 times 2 to the p, which is of course going to be bigger than 0. Now given this, since we know that p plus 1 times p factorial is p plus 1 factorial, we can rewrite this as p plus 1 factorial. And since we know that 2 times 2 to the power of p is 2 to the power of p plus 1, we can say that this is bigger than 2 to the power of p plus 1, which is what we wanted to establish in the first place. We wanted to have the form n factorial greater than 2 to the power of n for the next number after p, which is p plus 1. And we've done exactly that. Here we can see when n is equal to p plus 1, this statement that we've shown here is exactly n factorial being greater than 2 to the power of n, which is p plus 1. So therefore, we have proven it true for n equals p plus 1. So we can write here, therefore, true for n equals p plus 1. Given this, we can now state that by the principle of mathematical induction, this is going to be true for all of the values that we wanted. How can we do that? We can do that by going back to our base case and what we proved. We proved for our base case that it's true for n equals 4. We've now proved that if it's true for n equals p, where p is an element of the set that we want to find for, it is true for the next element. Combining these two statements together, combining statement 1, which is the base case, and statement 3, which is going to be the inductive step, we can say that since it's true for 4, it's going to be true for the next number, which is 5. Since it's true for 5, it's going to be true for the next number, which is 6. Since it's true for 6, it's going to be true for the next number, which is 7, and so on indefinitely. In fact, as we can see, this is covering all of the elements of the set that we wanted to find for, the set of n being an element of the integers and n greater than 3. As a final statement, we can say that therefore the statement we wanted to prove, which is that n factorial is greater than 2 to the power of n for n being an element of the set that we wanted, which is n being an element of the integers and n greater than 3, is true. So we can write that as our final answer, proven by mathematical induction. For our next problem, we're going to prove that the sum from r equals 1 up to n of r cubed is equal to n times n plus 1 divided by 2 whole thing squared. And we're going to show that this is true for all n elements of the positive integers. So basically what we're trying to prove here is that the sum 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed up to n cubed, where n is some element of the positive integers, is equal to n times n plus 1 divided by 2 whole thing squared. In order to do this, we're going to be using the same methodology that we did for the previous question, where we're going to first consider the different values of n, in this case, that we need to solve for. We're going to use that set of values in order to establish our base case and the rule that links the next step to the previous step. Using this, we're going to solve for the base case and find that it's true for the base case, and then given that it's true for some value which we're going to assume, we're going to show mathematically that it's going to be true for the next value as well. Using that inductive step and our base case, we're going to then show that it's true for all of the values in our set that we want to prove for. So considering the set we need to prove for, we need to prove for all n, which is elements of the positive integers. This means we need to show that it's true for n equals 1, n equals 2, n equals 3, and so on. In this set, the lowest number that we need to show for is n equals 1. So that would make a good base case. So what we're going to do first is to show that it's true for n equals 1. So to do that, we're going to consider n equals 1. Considering n equals 1, the left hand side is going to be equal to the sum from r equals 1 up to the value of n, which is 1 of r cubed. This means we need to take all the values of r from r equals 1 up to 1, cube them and sum them all together. In this case, from r equals 1 up to 1, there's only one value of r, which is 1. So therefore, the sum here is just the single value of r cubed added together, which is just 1 cubed, which is going to be equal to 1. As for the right hand side, RHS is equal to n times n plus 1 divided by 2 whole thing squared, where n is equal to 1, which is going to be 1 times 1 plus 1 divided by 2 whole thing squared. Simplifying this down, we can see that 1 times 1 plus 1 is going to be 2, and then 2 divided by 2 is going to be 1. So we have 1 squared, which is going to be 1. So the left hand side is equal to 1 and the right hand side is also equal to 1. So in this case, we can see the left hand side is equal to the right hand side, which is what we need for the statement to be true. So therefore, since, we can write down here, since LHS equals RHS, we can say that it's true for n equals 1. This is going to be our base case, so I'm going to label it as equation number 1. Next, in our methodology, we're going to assume that for some element of the set that we want to prove for, the statement is true. So for, in this case, some element of the positive integers, we're going to assume that the sum from r equals 1 up to that integer of r cubed is in fact equal to this, and given that, we're going to mathematically prove that it's also going to be true for the next value. So what we're going to do down here is going to be saying let n equals p, where p is some element of the positive integers in this case, and then for that value we're going to assume that our statement is true. So we're going to assume that the sum from r equals 1 up to that value of n, which is p, of r cubed is in fact equal to the value you get when you substitute n equals p, which is going to be p times p plus 1 divided by 2 squared. And given this assumption, which I'm going to call statement number 2, we are going to have to prove that it's going to be true for the next value of n, which according to our rule is going to be n equals p plus 1, since we want the next number to be 1 plus the previous number. So what we're going to do now is to consider n equals p plus 1 and then show that if we substitute here instead of p plus 1 and substitute here instead of p plus 1, we're going to have a true statement as well. So what we need to show is that the sum from r equals 1 up to p plus 1 of r cubed is in fact equal to, in this case substituting n equals p plus 1, we would have to have p plus 1 times p plus 1 plus 1 divided by 2 squared. So to do that, what we're going to do is write down, consider n equals the next value p plus 1. Now we need to start from somewhere. In my case, I'm going to start from the left hand side and move my way forward onto the right hand side. So I'm going to start with the left hand side and consider the left hand side LHS, which is going to be equal to the sum from r equals 1 up to p plus 1 of r cubed. Now as we did in the previous question, what we're going to do is to try to use the previous question's result, the previous statement's result, as in the statement at n equals p, and use this to try to prove for the next statement. In order to use this, what I'm going to do is actually break this sum from r equals 1 up to p plus 1 into the sums from r equals 1 up to p and the final term when r is equal to p plus 1. As in here, what we have is r equals 1, r equals 2, up to r equals p and r equals p plus 1. I'm going to break that sum into all the sums from r equals 1 up to p of r cubed plus the very last term, which I know is the value of r cubed when r is equal to p plus 1, which I'm going to write down as p plus 1 cubed. The reason I did this is so that I can apply the previous value's result into the next value. Here we can see I have the sum from r equals 1 up to p of r cubed in both the sum assumed equation number 2 and our new equation for the left hand side of the next value when n is equal to p plus 1. So what I'm going to do next is to substitute for this value here the equation that I had in equation number 2. So substituting equation number 2, I'm going to write from 2, we get that the left hand side is the sum from r equals 1 to p plus 1 of r cubed is equal to this sum, which is p times p plus 1 divided by 2 whole thing squared. Here you can see I'm directly substituting this bit into here, plus this term, which is p plus 1 whole thing cubed. Now what we're going to do is simplify this thing and see if we can get it into the form that we need on the right hand side, which is p plus 1 times p plus 1 plus 1 divided by 2 whole thing squared. So to do that, what I'm going to do first is expand this squared into these terms on the inside, from which I get p squared, so p squared, times p plus 1 squared, which I'm going to write as p plus 1 squared, divided by 2 squared, which I'm going to write as divided by 4. To this I need to add p plus 1 cubed, and I'm going to do a little smart thing. Since I know what I want in my answer is going to be having an n cubed, so n squared, and an n plus 1 squared, I'm going to factor out this p plus 1 cubed into a p plus 1 times a p plus 1 squared. By doing this, I can see that this term here has a p plus 1 squared as a factor, and this term here also has a p plus 1 squared as a factor, which I can factorize together. So when I do that, I can see I have a common denominator of 4. So here if I take the p plus 1 squared out, I have a common denominator of 4, which I can write down as a denominator of 4. On this side I have a p squared, and on this side I need to take this p plus 1 into the common denominator of 4, which means I need to multiply it by 4. Multiplying p plus 1 by 4, I have 4p plus 4, which I can then add as a 4p plus 4 as this thing's common factor. Now I have this expression here. What I'm now going to do is simplify this down. Here I can see I'm going to leave the p plus 1 squared as it is. I can see that I have p squared plus 4p plus 4. We know that this thing is equal to p plus 2 squared. If you don't know that, just try to do p plus 2 squared and you will see it eventually ends up with p squared plus 4p plus 4. So therefore, this expression here is equal to p plus 2 whole thing squared. So I'm going to write that down as p plus 2 whole thing squared, divide by 4, and I'm actually going to quickly write that 4 is equal to 2 squared. Now at this point we can see we have p plus 1 squared times p plus 2 squared divided by 2 squared. We can see that that whole thing is equal to just p plus 1 times p plus 2 divided by 2 whole thing squared. So I'm going to write that directly as p plus 1 times p plus 2 divided by 2 whole thing squared. And now we're almost at the solution, but we're not quite there yet, because for our solution we need the form n times n plus 1 divided by 2 whole thing squared. Currently for n equals p plus 1, we have the n here, we have p plus 1, but we do not have n plus 1 here. We kind of have it, but we don't have it explicitly. So what I'm going to do is to break this p plus 2 into a p plus 1 such that I can have the form n times n plus 1 divided by 2. So I'm going to do that. Doing so, what I get is p plus 1 multiplied by the factor of p plus 1 divided by 2 whole thing squared. At this point we can clearly see the pattern of n times n plus 1 all divided by 2 whole thing squared. And now we can see we have the pattern where n is equal to p plus 1 of what we wanted to find previously, which is n times n plus 1 divided by 2 whole thing squared. So I can write down an arrow like, underline like this and say that we're done with this solution and we have proven it for n equals p plus 1. So we can write here true for n equals p plus 1, which is our inductive step. I'm going to write that as statement number 3. And now we have shown our base case of n equals 1, and we've also shown that if it's true for n equals p, it's true for the next value, which is n equals p plus 1. Using this, I can now write that from 1 and 3, and I'm going to write some kind of statement here. I'm not going to write it here, but you will have to write it in your exam. By the principle of mathematical induction, since it was true for n equals 1, and when assumed true for n equals p was proven true for n equals p plus 1, we can say, since it's true for 1, and since we know it's true for the next number given that is true for this number, if it's true for n equals 1, it's going to be true for n equals 1 plus 1, so it's going to be true for n equals 2. If true for n equals 2, it's going to be true for n equals 3. If true for n equals 3, it's going to be true for n equals 4, and so on. Therefore, it's going to be true for all n which are elements of the set that we wanted, which is the element of positive integers. So I can write down as a final statement, therefore, the sum from r equals 1 up to n of r cubed is equal to n times n plus 1 divided by 2 whole thing squared for n elements of the set that we wanted, which is n element of the set of positive integers. Hence proven. For our next and final proof in this video, let's prove that 1 plus x to the power of n is greater than or equal to 1 plus n times x for x greater than negative 1 and n being an element of the positive integers. Now in this case, it might not exactly be clear which thing we're going to change when we're doing our induction hypothesis, but in this case it's going to actually be n. And the reason x needs to be greater than negative 1 will be shown as we solve this simple equation here. So to tackle this inequality, we first need to establish a base case. Here we can see that n needs to be an element of the positive integers, which means that n needs to be 1, 2, 3, 4, 5, 6 and so on. So therefore, n needs to start at least 1 and then has to go up by 1 each time. So from that set we can see that a good base case might be n equals 1, and a good rule for induction might be the next term is 1 plus the previous term. So for that, let's consider the lowest that we can go, n equals 1. So we can consider n equals 1. At n equals 1, the left hand side is equal to 1 plus x to the power of 1, which is 1 plus x. And the right hand side, RHS, is equal to 1 plus nx, which is 1 times x, which is 1 plus x. So therefore, since LHS equals RHS, we can say since LHS is equal to RHS, we can also say that the LHS is greater than or equal to the RHS. Since this condition holds, we can say that it's true for n equals 1. So we can say down here, therefore, true for n equals 1. Now that we established the base case, let's now move on to assuming that it's true for some value and then showing that it's true for the next value in that case. So what we're going to do is to let's say n equal p, where p is some value that satisfies our condition being an element of the positive integers like this. So you can say element of positive integers, and we also have the additional condition that x is greater than -1, which we need to carry around and solve our equation. So now, given these conditions, what we're going to assume is that this statement here is true, that 1 plus x to the power of n is greater than or equal to 1 plus nx. So to write that down, we'll write that 1 plus x to the power of p, in this case, is greater than or equal to 1 plus px. This is the condition that we're assuming to be true in order to prove the next one to be true. So now what we need to do is to consider the next value of n, which is going to be p plus 1. So next, let's consider n equals p plus 1. Considering n equals p plus 1, what we need to show is that the left hand side, which is 1 plus x to the power of n, is greater than or equal to 1 plus nx when n is equal to p plus 1. To do that, let's substitute the left hand side, LHS, which is equal to 1 plus x to the power of n, which is p plus 1. Now what we're going to do here, in order to substitute this thing on the left hand side, is to expand this thing outward as being equal to 1 plus x times 1 plus x to the power of p. This is of course true, since 1 plus x to the power of p plus 1 is equal to 1 plus x times 1 plus x to the power of p. Now given this, we can see that 1 plus x to the power of p is there in this equation. It's also there over here. Now given this, we can see, since 1 plus x is greater than 0, it's a positive value, and we can say that it's a positive value since x is greater than -1. We have a positive value times something on the right here. Positive value 1 plus x times 1 plus x to the power of p, which is some number that is greater than 1 plus p times x. So now, given this, we can write this equation at the top here, 1 plus x to the power of p, which is greater than or equal to 1 plus px, and say that if we multiplied both sides by 1 plus x, the inequality sign would not change direction, since this is a positive value, which would give us 1 plus x times 1 plus x to the power of p, which is greater than or equal to 1 plus px multiplied by 1 plus x, and that's that. Here, since 1 plus x is a positive value, since x is greater than -1, we can do this without changing the sign's direction. Now that we have this, we can see that on the left, this thing right here is exactly what we wanted to find, the left hand side that we intended, which is 1 plus x to the power of p plus 1. So we have 1 plus x to the power of p plus 1, which is greater than or equal to this thing, which is 1 times 1, so 1 plus 1 times x, which is x, plus px times 1, which is px, plus px times x, which is px squared. Now then, here we can see we have a 1, we have an x, a px, and a px squared. We can factorize this whole thing into a p plus 1 times x. Doing so, we get that 1 plus x to the power of p plus 1 is greater than or equal to 1 plus p plus 1 times x plus px squared. Now then, since x is greater than -1 and it's a real number, x squared is going to be a positive real number. Now, since x squared is a positive real number and p is some positive constant, since we assume that p is an element of the positive integers, we know that p times x squared is some positive value, as in p x squared is greater than or equal to 0. It could be equal to 0 since x could be equal to 0, since our only condition was that x is greater than -1 and 0 is greater than -1. But we know for sure that it is not less than 0 since x is a real number. Given this, we can now say that 1 plus x to the power of p plus 1 is definitely going to be bigger or equal to 1 plus p plus 1 times x, since this additional thing that we're adding here is either some positive value or 0. If it's 0, we can completely cancel it out and write this thing directly, and if it's not 0, it's definitely going to be some positive value, in which case it's going to be a greater than sign. So in both cases, the greater than or equal sign is satisfied. So therefore, we can finally write that 1 plus x to the power of p plus 1 is greater than or equal to 1 plus p plus 1 times x. This is what we intended to find, since what we wanted is 1 plus x to the power of n to be greater than or equal to 1 plus n times x. So therefore, this is true for n equals p plus 1. Now then, this is what we wanted for our inductive step. We wanted to show that given for it's true for n equals p, it's going to be true for n equals p plus 1. And for our base case, we know that it's true for n equals 1. So therefore, writing some statement here, we could say something like, by the principle of mathematical induction, since it's proved true for 1 and when assumed true for p was found true for n equals p plus 1, we can say, since it's true for 1, it's true for 2. Since it's true for 2, it's true for 3. Since it's true for 3, it's true for 4, and so on. So therefore, 1 plus x to the power of n is greater than or equal to 1 plus nx for all the n's that we found, which were all the n's that are elements of the positive integers, and also provided the condition that x is greater than negative 1. This condition is important. This condition would not be valid in this step here if x was anything less than or equal to negative 1. In the case that n is equal to x is equal to negative 1, we would have 1 minus 1, which is 0. So we are essentially multiplying both sides by 0, which is useless. And in the other case, if we have a negative number, we are multiplying the left side by a negative number and the right side by a negative number. And when you multiply an inequality by a negative number, the inequality sign needs to flip. So in any case where x is anything equal to or less than negative 1, this will not be valid. So therefore, we need the condition that x is greater than negative 1. And for that condition, n element of the positive integers will satisfy this inequality here. So that's going to be all for this video. Induction is quite a powerful concept. It can be used for much more complicated questions than this. However, within our syllabus, we generally only tend to use it for integer values of n or whatever. And in that case also, we generally tend to use it for quite simple laws like this. So that's going to be all for this video. I hope you enjoyed. Thank you for watching and goodbye.